Let's continue on with the final submodule on rotary bottom hole assemblies. In this submodule, we will list 4 of the 6 factors that might cause unanticipated directional performance from a rotary BHA and describe 3 contributing factors to BHA stiffness, stating which can be adjusted downhole. We will look at different types of build, hold and drop assemblies and which ones are preferred. Here we are examining the fulcrum or build principle and how weight on bit affects the trajectory of the wellbore. Starting with the diagram on the left, you can see the bit at the bottom labelled with bit tilt in blue. The hole direction is shown in red and the arrows indicate forces acting on the bit. When we apply weight on bit, it creates a tilt at the bit. This tilt generates a positive side force, also called the build force, that pushes the bit to increase the well inclination. At the same time, we must consider the negative side force shown here as the pendulum force, which tends to bring the hole angle back down. Increasing the weight on bit moves the tangent point closer to the bit. This enhances the bit tilt and strengthens the positive side force, reducing the unsupported weight that causes the pendulum effect. If the build force exceeds the pendulum force, the hole angle will increase, giving us a build tendency. Conversely, if the weight on bit is reduced, the pendulum effect dominates and the hole angle will drop. The key takeaway is that by carefully controlling weight on bit, we can balance these opposing forces and steer the wellbore in the desired direction. Now, let's look at the key factors that drive the build-up rate, or BUR, of a rotary BHA. The build rate is essentially the rate at which the wellbore angle increases per unit of depth, and it is controlled by both the BHA design and drilling parameters. The first significant factor is the distance between the near bit stabilizer and the first string stabilizer. Extending this distance magnifies the fulcrum effect, which generates a stronger side force at the bit and increases BUR. Weight on bit also plays a direct role. As weight on bit increases, the tilt force increases, encouraging the bit to climb upward. Hole inclination itself is another contributor, as a steeper wellbore amplifies the mechanical forces acting on the bit. Reducing drill collar diameter decreases stiffness, making the assembly more flexible and responsive to side forces, which again increases BUR. On the operational side, reducing rotary speed or flow rate, particularly in soft formations, also enhances the build tendency. The takeaway is that BUR is not controlled by a single element, but rather by a combination of design and operational choices. Engineers must balance these factors to achieve the required trajectory without creating excessive dogleg severity. The diagram summarizes the key variables that increase BUR. Arrows indicate the direction of influence. Increasing stabilizer spacing, weight on bit, and inclination all push BUR upward, while reducing collar diameter, RPM, or flow rate also enhances BUR. The effect of increasing weight on bit depends heavily on the type of BHA configuration being used. For a building BHA, adding weight on bit enhances the build tendency since it strengthens the side force that acts to tilt the bit upward. In contrast, for a dropping BHA, higher weight on bit can reduce the drop rate, countering the pendulum effect. This illustrates how sensitive BHAs are to weight on bit adjustments. The same action can have opposite results depending on whether the assembly is designed to build or drop inclination. From an operational perspective, it is critical for drillers to recognize how the assembly has been configured before making changes to weight on bit. Applying too much weight in the wrong configuration can lead to dogleg severity and unwanted trajectory changes. Conversely, insufficient weight on bit may result in inefficient drilling and an inability to achieve directional targets. When a near bit stabilizer, NBS, is under gauge even slightly, the impact is significant because of its close proximity to the bit. This reduction in diameter alters the side force at the bit, reducing build capability. In some cases, an under gauge NBS can even cause a build assembly to drop inclination unless high weight on bit is applied. For the second stabilizer, being under gauge makes it easier to establish a tangency point below the stabilizer. This change affects how side forces are distributed along the BHA. For hold assemblies, maintaining full gauge is particularly important to ensure zero net side force and a steady trajectory. The greater the undergauge condition, the more pronounced the effect on directional performance. The diagram compares full gauge and undergauge stabilizers. It shows how a small reduction in the near bit stabilizer diameter alters bit side forces, leading to reduced build or even drop tendencies. Now let's look at using an undergauge near bit stabilizer. Starting with the diagrams on the right, we have two assemblies A and B. In both cases, the near bit stabilizer is under gauge. That change in gauge alters the bit side force and produces a drop tendency in the hole angle, but the difference between the two is in the spacing of the second stabilizer. In assembly A, the second stabilizer is set further up, about 30 feet from the bit. This longer distance increases the fulcrum length, so the rate of drop is greater. In assembly B, the second stabilizer is only 10 feet above the bit. This reduces the fulcrum distance, so the BHA still drops, but at a slower rate. Now let's connect this to the points on the slide. First, using an undergauge stabilizer results in changes to the bit side force. A build type BHA fitted with undergauge will have less ability to build inclination. A lockup or pendulum type BHA will drop angle, as we see here, and the effect becomes more pronounced the greater the amount of undergauge applied. So the key message is both assemblies drop, but stabilizer spacing controls the severity of that drop. If the second stabilizer is under gauge, it becomes easier to get a tangency point below it. It becomes easier to build angle. The more under gauge, the greater the effect. In holding locked BHAs, an undergauge second stabilizer is usually deliberately included in the BHA. The objective is to reach a condition of zero net side force at the bit. BHAs designed for building inclination rely on configurations that maximize side force at the bit. These assemblies typically feature longer spacing between the near bit stabilizer and the first string stabilizer, creating a strong fulcrum effect. When looking at the two BHA on the right, one has a long spacing between the near bit stabilizer and the second stabilizer, which is under gauge. The second BHA, annotated as B, has an undergauge string stabilizer much closer to the near bit stabilizer, which BHA will deliver more build. Well, BHAA should build more because the longer spacing increases the fulcrum effect. Hole gauge is another critical factor affecting BHA behavior. In an enlarged hole, such as a washed out section, stabilizers are no longer in firm contact with the borehole wall, which weakens their ability to guide the bit. For a building BHA, this reduces its ability to generate side force, leading to a lower build rate. In extreme cases, the assembly may even drop inclination despite being designed to build. Conversely, for a dropping BHA, hole enlargement can diminish the pendulum effect, making the assembly less effective at reducing angle. A gauge hole, by contrast, ensures stabilizers engage properly, enabling the assembly to perform as designed. For directional drillers, recognizing hole condition is crucial. Poor hole cleaning, excessive flow rates, or soft formations can lead to overgauge sections which complicate trajectory control. Here are examples of bottom hole assemblies commonly used for building inclination. First, let's look at BHA number 9. This design is capable of achieving very high build rates, on the order of 5 degrees per 100 feet or even higher. Of course, the actual performance depends on factors such as formation geology, existing inclination, hole diameter, collar size, and the drilling parameters applied. By contrast, BHA number 3 is used where we want only a slight to medium build tendency. The response depends largely on how much under gauge the middle stabilizer is and how sensitive the assembly is to weight on bit. It's important to note that in any build-up BHA, the near bit stabilizer should always be very close to full gauge. This becomes even more critical as the hole size gets smaller. With regard to stabilizer spacing, as the distance to the second stabilizer increases, the build-up rate also increases. The strongest build response comes when the second stabilizer is positioned about 90 feet from the bit, with a third stabilizer placed relatively close behind. In this configuration, the sag that develops to the right of the second stabilizer is counteracted by the third stabilizer, which enhances sag to the left, and that results in a higher build rate. So the takeaway is that both stabilizer gauge and spacing are key levers in controlling the build-up response of a BHA. In practice, slight changes in hole inclination often occur, even with a good choice of locked BHA. However, the objective is to get a complete bit run without needing to pull out of hole for a BHA change. Experience in a location should give the DD the data for fine-tuning the BHA. Reducing the gauge of the second stabilizer gives the same result as leaving the stabilizer alone, but increasing the distance between it and the near bit by a certain amount. However, for directional control purposes, the former approach is better. The reason is that using an undergauge stabilizer and placing it closer reduces the amount of sag, making the response more predictable when applying weight. The forces are designed to be net neutral and the BHA will hold. Lock-up BHAs account for the biggest percentage of hole drilled in deviated wells. Thus, the DD's judgment and expertise in BHA selection are vital in saving trips. The issue with a locked BHA is that gravity still prevails. Therefore, a locked BHA is best suited for near vertical trajectories, whereas BHA 6 is best for tangent sections. Locked-up assemblies are built to maintain inclination by balancing side forces through stabilizer placement and collar stiffness. Their performance depends on several factors. First, hole size. Larger or washed-out holes reduce stabilizer contact and compromise control. Second, the distance between the near bit stabilizer and the lower string stabilizers. This spacing dictates the fulcrum and pendulum effects, influencing whether the BHA holds steady or begins to deviate. Third, the stiffness of the collar directly above the near bit stabilizer is critical, as stiffer collars provide greater resistance to bending, keeping the bit on trajectory. Fourth, the gauge of stabilizers, since undergauge can be used to neutralize drop tendencies. Finally, drilling parameters such as weight on bit, RPM, and flow rate directly affect the performance of this assembly. A locked-up BHA is often used in tangent sections, where steady drilling with minimal deviation is required. Its success depends on keeping all these variables within planned tolerances, ensuring that the assembly drills straight and maintains inclination effectively. A variation to this design is to use a variable gauge stabilizer or VGS in the second position. A variable gauge stabilizer can alter its OD between full gauge and undergauge. This is commonly done by cycling the pumps. So when the surveys indicate that the BHA is starting to drop, the DD will cycle the VGS into the undergauge position. If the BHA starts to build, this can be mitigated by changing to a full gauge setting. Dropping BHA relies on the pendulum principle, where the bit naturally hangs lower than the string due to gravity. In these assemblies, the near bit stabilizer is often under gauge, reducing the upward side force and enhancing the pendulum effect. While they can effectively reduce angle, dropping BHAs are less controllable than build or hold designs. Their performance depends heavily on hole gauge and formation type. Washed-out holes can increase their drop capacity, while harder formations may resist angle reduction. For this reason, drop BHAs are often considered corrective rather than standard tools, deployed only when trajectory corrections are required. In practice, engineers prefer semi-drop assemblies, which blend elements of hold and drop design, offering greater stability while still achieving a downward tendency. It is essential to monitor surveys closely when using drop BHA, as unanticipated deviations can occur quickly. Despite limited application, understanding their design and behavior is crucial for directional drillers, ensuring they are equipped to correct inclination issues efficiently. The diagram shows that the removal of the near bit and the increase in the spacing to the second stabilizer increase the pendulum effect and thus the drop tendency. Bit selection significantly influences the directional behavior of rotary bottom hole assemblies. Roller cone bits generally have a tendency to walk to the right. In softer to medium formations, long tooth bits enhance this walk tendency, while short tooth bits in harder formations reduce it. These bits often require higher rotary speeds, though that shortens bearing life. PDC bits, by contrast, exhibit little to no natural walk tendency. If a PDC does walk, it will turn right due to the reactive torque. Their gauge length plays a significant role in trajectory. Long gauge PDCs are effective for holding inclination and direction. In contrast, short gauge PDCs generate more build than roller cones. PDC bits are also suitable for pendulum assemblies, where stability and predictability are needed. However, in build assemblies, they can compromise the build rate when using higher RPM and low weight on bit. Also, at high RPM, they can cause high surface torque. The interaction between bit type, formation properties, and BHA design is crucial. Formation dip can strongly influence the trajectory of a rotary BHA, sometimes overriding design intent. When the dip angle exceeds 45 degrees, the bit tends to drill down dip, since this represents the path of least resistance. Conversely, when dip is below 45 degrees, the bit typically drills up dip, again following the easier path. This natural tendency occurs because drilling follows rock stress and bedding planes. In practice, this means that even a well-designed BHA may exhibit unanticipated performance if formation dip is not accounted for. Engineers must study geological data, including seismic and offset well records, to predict dip effects. When drilling steeply dipping formations, adjustments may include modifying stabilizer placement, bit type, or drilling parameters to counter natural deviation. Let's review the key learning objectives. By now, you should understand the fundamental concepts of rotary BHAs, including how stabilizer placement, collar stiffness, and gauge conditions influence performance. You should be able to describe the fulcrum and pendulum principles, explaining how they create build or drop tendencies. We've also looked at drilling parameters weight on bit, RPM, and pump rate, and how they interact with BHA design to influence trajectory. You should now be able to list at least 4 of the 6 factors that cause unanticipated directional performance, such as stabilizer size, hole enlargement, bit type, or formation dip. Finally, you should be able to describe 3 contributors to BHA stiffness and identify which ones can be adjusted downhole. These concepts form the basis of effective rotary BHA design and real-time trajectory control. The key message is that rotary BHAs are not static systems. They respond dynamically to drilling parameters, hole condition, and formation forces. By integrating design knowledge with operational awareness, you can predict behavior more accurately, reduce unplanned deviation, and optimize drilling efficiency. Thank you for working through this module on rotary BHA design. Please progress to the quiz.